Hey guys, we're going to look at number 5 in section 4.6 of Achieve. Section 4.6 really kind of summarizes or synthesizes together sections 4.3, 4.4, and 4.5. So it's going to take all those things together and kind of put them all together at one time. So it's kind of a review in a sense of those things. So you've got in 4.3, you're looking at the first derivative, which tells us where the function's increasing, decreasing, and where we have any local extrema. Section 4.4 deals with second derivative, tells us where we're concave up, concave down, and where we have any points of inflection. And then, of course, section 4.6 deals with L'Hopital's rule, which helps us in finding limits where we could be finding either vertical asymptote or horizontal asymptote, right? Horizontal asymptotes being limits at either infinity or minus infinity. Okay, so let's take a look at this particular function here that we're going to analyze. Again, very similar to the one that you have, hopefully, just the numbers maybe changed. Maybe this coefficient changed a little bit. Just to start off with, we're going to be dealing with this function. Just have you note the domain is all real numbers, and the domain of any exponential function e to the x, in this case it's e to the negative x squared, because the output is always a positive number. The domain is all real numbers, even though e to the negative x squared really is what 1 divided by, this little piece right here, just that little piece right there is 1 divided by e to the positive x squared. We're still good because e to the x squared is never equal to 0. It's always going to be a positive output. The exponential function's range is values greater than 0. Okay. And then we multiply by 5x. So no problems there. Domain is all real numbers. Basically, in this problem, we're going to find transition points. Okay, that's anytime we have a change in either from increasing to decreasing, decreasing to increasing, right, at a local max or min, or if we have, or it could be also across a vertical asymptote. So transition points, we could have a transition across a vertical asymptote, but the points are actually points on the graph of the function, so we wouldn't include vertical asymptotes, although we would want to check between and beyond any vertical asymptotes as far as a sign check on the first derivative. Transition points are also where the second derivative changes sign. In other words, we have a change in sign in the rather change in concavity from concave up to concave down, or vice versa. So we'll find all the transition points, or essentially we'll find all the potential transition points, and then we'll do a sign check to confirm where those occur. Once we have the sign checks, then we just give all this information. This is the sum. This is 4.3 and 4.4 and 4.6, all 4.3, 4.4 and 4.5 rather, excuse me, all pulled together. So, finding all these things, locations of max mins, intervals of increase, decrease, location of any points of inflection, intervals where we're concave up and down, and then that horizontal asymptote. And then they want you to graph it, and that's pretty easy actually in Achieve. They give you the utility. You just type in the formula and it graphs it for you. So just basically retype in the actual function. Okay, so let's begin the process. First of all, we need to find the first and second derivatives, and find the critical points and the points where the second derivative is 0 or undefined. So when I take the derivative of this function, I've got 5x times e to the negative x squared. I'm going to have to use the product rule. So the derivative of 5x is 5 times e to the negative x squared plus 5x times the derivative of e to the negative x squared. Well, that's the chain rule, right? So you've got e to the u, so where u is negative x squared. So the derivative of e to the u is e to the u times the derivative of u, the inner function, derivative of negative x squared is negative 2x. I get negative 2x times e to the negative x squared. So clean this up a little bit, multiply these two things together. I get 5 times negative 2 is negative 10. X times x is x squared, e to the negative x squared. I'm going to go ahead and factor. That'll help me find out when the derivative is 0. Factor out a 5, right? And I got a common e to the negative x squared term. So I go, factor. So I pull that out. That leaves me 1. And then 5 out of negative 10 leaves me negative 2. and then the x squared. So notice that this part is never 0, right? Remember, e to the negative x squared is always a positive quantity, but the first derivative is 0 when 1 minus 2x squared is 0. That's going to occur when x squared is a half, or when x is either plus or minus 1, the square root of a half, or 1 divided by the square root of 2, which we can rationalize if we want to and write it in this way. So I'm not sure how Achieve, might accept either of these answers, but just to make sure you're aware of that. Okay, so those are potential transition points, because we could have a change in, increasing and decreasing, or decreasing and increasing. Could have local max or mins at those points. Okay, and notice the derivative again is never undefined. Its domain is all real numbers as well. Now to find the second derivative, we take the derivative of the derivative. I'm actually going to work off of this one before I factored. So taking the derivative of the first one, it's 5 as a constant multiple pulled out. Derivative e to the negative x squared, well, we did that just here a minute ago. That's negative 2x e to the negative x squared by the chain rule. So the derivative of this one is right there. And then minus, and I put in parentheses because I want to make sure I distribute that negative through, 10x squared times e to the negative x squared. I've got to use a product rule on that. So I take the derivative of 10x squared, which is 20x down here, times e to the negative x squared, plus 10x squared times the derivative of e to the negative x squared. Again, that same one we've seen by the chain rules, negative 2x e to the negative x squared. Clean this up a little bit. 5 times negative 2 gives me negative 10. And then I distribute the negative sign through. So I've got to multiply this thing by negative 1 and this thing. So this is easy, negative 20 x e to the negative x squared. And then here I've got negative 2 times 10. That's negative 20 times that negative is positive 20. X squared times x is x cubed, e to the negative x squared. Combine, if I can, and I can, these two are like terms, notice. So negative 10 x e to the negative x squared minus 20, same expression. So negative 10 minus 20, negative 30 plus that. Okay, so there's my second derivative. Let me go and factor. I'm going to factor out a negative 10 from the negative 30 and 20. I got an x here and an x cubed. I'm going to pull out an x, and then e to the negative x squared. I'm going to factor that out again. So that leaves me a positive 3 because I pulled out a negative 10, and it leaves me a negative 2 because I factored out a negative 10 from positive 20. I pulled one of these x's out from the x cubed, leaves me x squared. Okay, so now the second derivative is equal to 0. Well, e to the negative x squared, that's always positive, but x could be 0. So when x is 0, the whole thing is 0. Or when this stuff, 3 minus 2x squared, is 0. That's when x squared is 3 halves, right? And then plus or minus square root of 3 halves would be the value of x. So I've got these values here, this value, and these values. Those are the possible transition points. Okay. So how do we know for sure if they're transition points? Well, we do a sign check of the first and second derivative. I'm going to do all that together in one, putting these points down. And here's the way I do this, and you could use a table of values, whatever is easier to organize. This may be a little confusing, but for me, kind of helpful to put it all together. So here's my real number line. My points where my first derivative was 0 is plus or minus the square root of 2 over 2. By the way, if you use a calculator, that's about square root of 2 over 2 is about 0.707, just to get an idea of where these numbers lie. Of course, 0 was one of the values where the second derivative was 0, and then plus or minus the square root of 3 halves also was where the second derivative was 0, and that's about 1.22 there. So you can kind of see in order how to place these in the correct order. You want to list them correctly from smallest to largest. Okay, so the sign of f prime, well, it's 0 at these 2 points. Remember, that's what we found out before. And then I just need to check the sign of the first derivative. Well, in between, I have 0. So I can check the first derivative at 0. Here's the first derivative. Going across there. Again, you can use your calculator to do this, but I mean, I can do this in my head. If I plug in 0, e to the 0 is 1. So that's, again, this is always positive, by the way, no matter what x is. It doesn't matter that there's a negative here. E to the negative 1 power is just 1 divided by e. It's a positive number. So this always is positive. But when I plug in 0 here, then 1 minus 0 is positive 1. It's positive. So the first derivative is positive in between negative square root of 2 over 2 and square root of 2 over 2. And I've kind of got these vertical dashed lines going up as potential transitions, but I go ahead and put a plus on either side of that dashed line just to, but it's increase, derivative is positive, function's increasing over that interval. And then I check a number like back here, I could choose like -1 is less than -0.707. If I plug in a -1 and square it, I get +1. 2 times +1 is 2. 1 minus 2 is a negative. This is still positive. So the overall result is negative for the first derivative. Same thing if I plug in x equals +1. And so because of that, I get negatives for these two regions here for the first derivative. Second derivative is in black up here is 0 at 0 and at plus or minus square root of 3/2. And then I do a sign check for that. I'm not going to go into all the detail, but if I plug in like something less than -1.22 for this interval, try -2. If I plug -2 into the second derivative, here's the second derivative. So here's, I'll do it in this form here, the final form. If I plug in -2 for x here, I get -10 times -2 is +20. This is always positive, so this whole thing will be positive. If I plug in -2 here, I get 4 times 2 is 8. 3 minus 8 is -5. This will be negative. This will be positive. A positive times a negative is going to be negative. Again, if you just want to enter that into your calculator, plug in the numbers, and just see whether it's positive or negative. That's fine. So it's negative there. And then it'll be positive between negative square root of 3 over 2 or about -1.22 and 0. And then it'll be negative between 0 and the square root of 3 over 2. And then it'll be back to being positive for values greater than square root of 3 over 2. So you can verify and check that hopefully. And that's the sign. Now I add in just the shape, and the book talks about this, right? The minus shape. The minus comes from the sign of the first sign comes from the derivative, second sign from the second derivative, right? First derivative, second derivative. So negative means what? Means negative first derivative means decreasing, negative second derivative means concave down. So that's the shape, decreasing concave down. First derivative negative, second derivative positive means decreasing concave up. Positive, increasing, right? First derivative positive means its function's increasing. Second derivative positive means it's concave up, increasing concave up. Plus minus, increasing concave down. And then minus, again, decreasing concave down, minus plus, decreasing concave up. And you can see if you just take these and connect these pieces, this is sort of what the graph looks like. Okay, this is what the graph looks like. It's going down, and it's got this curve going up, and then up this way. And then if you just sort of click and drag these pieces together, you get a rough idea of the shape of the graph. We do need to know about any horizontal asymptotes. There's no vertical asymptotes, again, because this function's domain is all real numbers. There's no potential problems there. We can quickly get all the information from the graph. It has a local min where by the first derivative test, since we change from negative to positive at negative square root of 2 over 2, right? Decreasing to increasing for the function, right? You can even see it right here. We've got a local min, right, at x equal negative square root of 2 over 2. The first derivative changes sign from positive to negative at square root of 2 over 2. So we have a local max there, right? Local max. Points of inflection occur where we have a change in sign of the second derivative. Well, that occurs at negative square root of 3 over 2. It occurs at 0, and it occurs at positive square root of 3. So all our potential transition points indeed become transition points. So those are all the transition points. So we have points of inflection at all those points. Okay, we're increasing where the first derivative is positive. So from negative square root of 2 over 2 to positive square root of 2 over 2. We're decreasing on the interval where the first derivative is negative. So minus infinity up to negative square root of 2 over 2 and square root of 2 over 2 to positive infinity. We're concave up where the second derivative is positive. So second derivative is positive between negative square root of 3 over 2 and 0, and positive here, square root of 3 over 2 to infinity. And that's what I have here. And then similarly, f is concave down on the intervals where the second derivative is negative, and that occurs on these other two intervals. Okay, so that all comes. So on the test, it's imperative that you give me something like this, a sign check. I prefer to do them together in this case. But whatever, any of these things I'm asking for, if I'm asking for these, you have to, of course, find the first and second derivative as needed, but then do a sign check like this. Very important that you do that for support. Okay, horizontal asymptote, do we have one? Well, we take the limit as x goes to infinity. That's a horizontal asymptote at infinity for the function. So remember, the function is 5x e to the negative x squared, which I'm just going to rewrite. Remember, e to the negative x squared is 1 over e to the x squared. So I'm going to rewrite this as 5x divided by e to the x squared. Same thing, same thing. But now we see as x goes to infinity, 5x is going to infinity. And e to the x squared, since x squared is just getting bigger and bigger and bigger, that's going to infinity as well. So it's infinity over infinity. That's an indeterminate form, but it's a L'Hopital rule form, right? So here's L'Hopital's rule from section 4.5. I can maybe find this limit by what? The limit of what? The derivative of the top, what's the derivative of 5x? That's 5. Over the derivative of the bottom, what's the derivative of the bottom? Well, that's the chain rule again, right? E to the u. So it's e to the u times the derivative of u, which is 2x. So 2x e to the u. 2x e to the x squared. Okay. Now this form is not indeterminate because as x goes to infinity, what's the top going to? 5. It's constant. It's just 5. 5, 5, 5, 5. All right. The bottom is what? X is getting bigger. E to the x squared, that's getting bigger. That's going to infinity. 5 divided by infinity is determinate. That's 0, right? In other words, 5 divided by a larger and larger number is going to get closer and closer to 0. So that means the function as x goes to infinity is getting closer and closer to 0. So y equals 0, which is the x-axis, is a horizontal asymptote. By the way, we get the same if we go to x to negative infinity because I'm squaring x squared down here, right? And so this e to the x squared will always still be going to positive infinity. X will be going to negative infinity in that case, but we'll have 5 divided by negative infinity. That's also going to 0. Even 5 divided by a bigger and bigger number in absolute value, even though it's negative, is still going to 0. Okay, we're just approaching 0 from the negative side, so to speak. Okay, so that is all the analysis we do, and then we want to graph the function. And let me just go to achieve real quick. Give me a second to do that. And here you see I've already entered in this function. When you go to type it in, they give you the little template, I think, appears where you can put in the exponents and everything. So use that. But once we get that, it will automatically graph it for you. And here's the graph, and we can zoom in a little bit with that, and you can check and confirm. So for instance, we said we had a local minimum at x equal negative square root of 2 over 2, which was about negative 0.70. And we can see we have a local minimum right here. And indeed, this is negative 2, so negative 1 is here. So that seems reasonable. It seems close to about negative 0.7 something. And then also at positive 0.7, we said we had a local max. And we said we were decreasing, right, for values less than negative square root of 2 over 2, increasing between square root of 2 or negative square root of 2 over 2 and positive square root of 2 over 2, and then decreasing again. So that's consistent. And then the concavity, we said we had a change in concavity at 0. Well, it certainly seems that case because this looks concave up, right? You see the smile. The derivative is increasing over this interval. And then here, the frown, right, we're derivative going from left to right is decreasing, so we're concave down. So 0 seems like an inflection point. We also have a point of inflection right about here, which is 1 point something. In fact, we said it was at the square root of 3 over 2, which is 1.22. And there we're changing from concave down to what? Here, it's concave up. See the part of the smile here. And so there's an inflection point there. And similarly, there's an inflection point here from concave down to concave up. And you see the horizontal asymptote as x gets very, very large, we're getting closer and closer to the x-axis to y equals 0. And it looks like it almost merges. It actually, we know it never actually touches the x-axis. It gets closer and closer to it, but never becomes exactly 0. It's always, something positive, but getting closer to 0. And similarly here, we're approaching 0, but it's always negative. It's always below the x-axis. Okay, so there's a lot going on in these problems in section 4.6. That's understandable as it sort of synthesizes all those things that we learned in the previous 3 sections. Okay, so take your time through these and let me know if you have questions for other problems.